there for in case you need to look back at it. All right, so our goals today is to compute and interpret the coefficient of determination. And again, that is known as our R squared value is what that is known as. So I'm going to write that in there real quick. I like using the capital letters. So I think it's usually listed as a lowercase, but R squared. It's also, that's the way it looks on the calculator when we see it printed out. So we're going to go through, learn how to compute it and interpret it is what we're going to go through today. We're also going to practice doing some of those least squares regression lines again and getting the R values. That way we just kind of recap what we did in the last unit, last week or last section. The coefficient of determination, or the R squared value, measures the proportion of total variation in the response variable that is explained by the least squares regression line. So what does that mean in a nutshell? The coefficient of determination is a measure of how well the least squares regression line describes the relation between the explanatory and the response variables. If the R squared value is closer to 1,
teachers, please excuse this interruption, but we are still missing a lot of students for the English testing. Students, if you have English 1 or 2, first or second block, you need to report to your testing location now, please.
The closer R squared is to 1, the better the line describes how changes in the explanatory variable affect the response variable. So on our calculator, when we do this by hand, we're going to see it as a decimal, is what we're going to end up seeing. If you think back to our last lesson where they gave us those little mini tab printouts, and it actually had on there R-SQR, and that was basically your R squared value, is on those little mini tab reports. So that one typically is listed as a percentage, is what we see it listed at on those little reports. But when we're doing the calculations with the TI-84, it'll be a normal looking decimal, is what it's going to be looking like. Now, here are some characteristics about it. The coefficient of determination is a number between 0 and 1. So it's positive. Okay, it's between 0 and 1. Inclusive means it could be 0 or it could be 1. Okay, if you ever see the word exclusive, that means 0 and 1 are not options. Okay, so that's the difference between when you see terminology in statistics says inclusive and exclusive. Inclusive means I can include the little n numbers as potential values, whereas exclusive means we leave those n numbers off. Okay, so basically, nutshell, R squared has got to be positive, somewhere between 0 and 1. If R squared is equal to 0, that means the least squares regression line has no explanatory value, so it doesn't explain the variation that's happening in the response variable, is what that's the meaning. If R squared is equal to 1, then that means that the least squares regression line explains 100% of the variation in the response variable that's taking place. And again, 100%, typically that would mean, as a least squares regression line, a straight, perfect linear line. Like straight, all the dots are in a nice diagonal pattern, not any spacing vertically away from the line of best fit or the LSRL. So to get us kind of warmed up here, we have 3 different data sets, so this one's going to take us a little bit of time. We need to find for each one of these, for data set A, B, and C, we need to find out what the LSRL, so what's the least squares regression line, what is the R value, and then what is the R squared value for each data set. So I'm going to start working on this carefully, and you guys can work as fast as you want ahead of me on it as we do it. So I'm going to go back into the calculator, hit stat, hit enter on edit, and I'm going to start typing in. I'm going to do X is L1 and Y is L2. So now we're just going to be careful typing stuff in. I'm going to do one line at a time. All right, looks like I got mine in there okay. So I'm going to go stat, calculate, down to option 4, lin reg. Whoops. Stat, calculate. There you go. Option number 4, lin reg. I got my stuff set up in L1 and L2. Fantastic. Arrow down. Hit calculate. Oh, notice what I didn't turn on. I did not turn on the stat diagnostic feature. So for the LSRL, well, let me just do that. Mode, stat diagnostic. Hit on. And then go back in and do my lin reg.
How do you do the stat thing?
Hit mode, and then arrow down about 3/4 of the way down. You'll see stat diagnostic. And you'll arrow to the right and click on. It's after like Stat Wizard or something like that. So my LSRL, my least squares regression line, would be y equals 4.2159 plus 1.2992x. The slope is the A. They have it on the screen there. Sorry. Obviously, we're having Wi-Fi issues because what's going on this morning? Probably some online test, and it's messing the Wi-Fi up now. I write my slope after. I write the y-intercept first. My AP kids, they have to write it that way, so that's why I write mine in that fashion. It's okay to write 1.2992x plus 4.2159. That's okay. So now, what are our values? Our R squared value was 0.99988. Our R value is a 0.99994. All right, well, for one, I haven't drawn a scatter plot yet. We could. I'm anticipating with that strong of an R value and that strong of an R squared value, our line is probably going to be a nice diagonal line going up from left to right. It's going to be a pretty nice, straight line, very little deviation vertically away from it. So I'm just curious. I'm going to go over there and look at it real quick before I get rid of that data. You can keep all that data in there if you want. We can do that. We can just put the other ones in like L3 and L4 and L5 and L6, and then we can compare all those if we want to. So with that in mind, I just want to see what that scatter plot looks like. Second stat plot. Let's turn that sucker on. Go over. Let's see. The very first one is a scatter plot, so we can just hit graph. And then I'm going to hit zoom 9 for zoom statistics. And that is a pretty nice straight diagonal line. So that, to me, it makes sense to have that strong of a correlation coefficient of 0.9994. And when we look at the coefficient of determination, almost 100% of the variation is in the response variable is explained by that regression line. So by the explanatory. All right, so I'm going to go back in here and I'm going to go into L3 and 4 and I'm going to put in the next column of data. So oh, you know what I just realized? You guys may have realized this as well. What do we notice about the Y values in each one of these? Yeah, they're the same. So after this, for the next one, I'm gonna speed stuff up. I'm just gonna tell it to take the L2 column and copy it down, just to make my life quicker. Where did I leave off at? 8.9, then 15, and then 4.8, 6, 14.9. 11.9, 9.8, 15, 4.7, and 13. All right, and then now I'm going to go stat, lin reg, and now I'm going to change my columns to second L3 and second L4. Go down and hit calculate. So now that one, I'm going to change up colors here. For the data set B, my LSRL is y equals 4, again, I'm going to do mine the other way, 4.84377 plus 1.17967x. You don't have to take them out that many decimals, but just make sure you go accordingly. I'll tell you on a test how far to take it out. My r squared value is 0.9473. My r value is 0.9733. Okay, so notice with that one, the r squared value came down some. It's not a perfect 99%. It's down to 94%. There is a decrease there. So 94% of the variation in the y value, the response variable, is explained by that explanatory variable. We still have a nice, strong, positive linear correlation with that r value. And then now we're going to go data set C. So I'm going to go back in here and enter. And in column L5, I'm going to type in that column there. And I'm going to do a shortcut on the next column. All right, so my shortcut is once I get to column 6, I'm going to go up to the column header, and I'm just going to tell it to be equal to column L2. So I'm just going to do second L2, and when I hit enter, it's going to take all those L2 values and put them down there for me. And so that just speeds up me not having to type in those Y values again, since we're using it again. Again, you can go up to a column header, type in an equation, whatever, and then it will execute it on all the values whatever you're doing the thing on. So now that that's set, I can go in and say stat, calculate, lin reg. I need to change it to column 5 and column 6. Go down to calculate. And then on this one, we have y equals 8.14636 plus 0.43675x. So my slope is 0.436. Now notice what happens to our r squared value. R squared is down to a 0.0939. And our r value is a 0.30647. So I'm gonna go ahead and just swipe the. I'm gonna leave the calculator there for a second. So as I look at these things here, that is really weak. Here we got a really weak. We got a weak positive linear correlation going on here. That R value going from the topic last section. Notice our coefficient of determination. Only 9% of the variation is explained by that least squares regression line. That's what that's saying. 9% of the variation in the response variable. Now we're going to look at a true interpretation here as a definition in a moment. 9% of the variation in response is explained by the explanatory variable. So to me, again, with that low of a R value, I'm thinking, okay, it's not going to have a nice, strong linear pattern. It's going to look kind of almost be a weak. It's going to be almost like a no correlation. It's going to be really wide, is what it's going to look like when we look at those dots. That's what I'm thinking. Now we can't graph all of them at the same time, but we can go in there and turn each stat plot on and off for the different columns to get an idea of what the graph would look like for each one of these. We don't want to leave all the stat plots turned on, because what's going to happen is you'll have just a whole bunch of dots on the screen, and you can't tell which one's which. Okay, so if you wanted to look at them, you would turn each one on and off to look at it, is what you would go through and do. We can do that if we want to. We don't. It just all depends on what you're doing. Again, we looked at the first one. Let's see. You can actually, if you wanted to, when you do the least squares regression line, if you want to see the equation, if you go in and do your linear regression, when you get down to where it says store reg EQ, you can actually, on the store reg EQ, tell it where do you want the equation to go? Where do you want that LSRL to go in the Y graphing feature? So it'll draw that line for you. And so if you do alpha trace, then you can pick where you want it. So if I say, put it into Y1, when I go to graph this equation, it's actually going to go through and put that line on there for me and stuff for that set of data. So as I go through here, let me hit calculate. All right, and then I hit graph. And now with that in mind, I still have stat plot 1 turned on. So I need to turn off stat plot 1, which is the first set of data. And then I'm going to go into stat plot 2 or 3, and I'm going to tell it to do it on that L5 and 6.
How do you turn on the dots?
When you go into stat plot and you hit turn it on, it should automatically be the squares, and then you choose plus signs or whatever. So if you do second y equals, and then you choose one of the ones to go into, it's toggled off. Just click enter on, and then that should put it on there. So here's what that last picture looked like for that last set of data. There's the LSRL. There's the least squares regression line. Notice how much variation we have vertically away from that least squares regression line for those data points. That to me makes sense why we saw such a low R value of 0.3. Now, as we learn the definition of the correlate, how to do the coefficient determination, how to interpret it, right now we know 9% of the variation is explained by the explanatory variable in this situation. That means 91% is explained by something we don't know what. There's 91% of the variation is caused by something else. Maybe it's some lurking variable. There's something else out there causing stuff to take place. Okay, and we just don't know what it is. If we think back to last week, we had an example of the golf club. They were doing the club head speed and how far they hit the golf ball. They try to do it on a perfect sunny day, no wind, to try to reduce those variables. If we go out there today, it's raining outside, it's pouring, and if I go out and do that club head speed test with the ball, is the ball going to travel as far with it raining? Probably not. Okay, and is there wind outside? Is the wind coming at where I'm hitting or from behind where I'm hitting? That's going to affect how far that ball travels. And so those are the things that would be the lurking variables for that are not explained by the explanatory variable. I put a little I put a little summary output for the mini tab here, where they show, hey, here's our R squared value right there. So that's that 80. So in that case, it would be 88% of the variation is explained by the explanatory variable, which means roughly 11% is not explained. Something else is causing that variation. 11%. Something else is causing the variation. Again, if we had a more concrete example like word problem, then we could be more specific of what could be part of those lurking variables. So that was kind of get us warmed up, and now we get to kind of go into it a little bit more. So here we got a problem. The old faithful, the other old faithful. Perhaps you were familiar with the one in Yellowstone. There's another one. It's in Napa Valley, California. The following data represents the time in minutes between eruptions and the length of eruptions for 9 randomly selected eruptions. The coefficient of determination is 83%. Provide an interpretation of this. So what we would say is that 83% of the variation in eruption length, because again, that's our Y variable, our response variable, eruption length is explained by the time between eruptions. %, of the variation in eruption length is unexplained. And I'm going to say because of some lurking variables. Again, we're not geologists in here. I took one class in college on geology, maybe 2. I wouldn't call myself an expert, but there's a lot of stuff that goes into plate tectonics and those kind of things that would cause our Old Faithful or this case this one erupting when we look at pressure being built up and so forth. So whatever those are, we basically are lurking variables. There's other things out there dictating the length of that eruption, not just the time between it. Okay, we know that they've got enough data to say, hey, as the time between eruptions increases, the length of the duration of the eruption, how long does it go? Is it increasing or decreasing the more time between? We think about just in case, hey, it's pressure being built up. So to me, as more time goes by between eruptions, that means there's more pressure being built up, which means the length of an eruption when it eventually happens will probably be longer when there's more time for it between those eruptions, because it's building up more and more and more pressure. Okay, whether that's the case, got no clue, because I'm not a professional geologist and plate tectonics person. So next example, a concrete cures, it gains strength. The following data represents the 7 and 28-day strength in pounds per square inch of a certain type of concrete. The coefficient of determination is 57.5%. So they typed in all that stuff, did that least squares regression line stuff, and they've got that what that number was. They asked us just to provide an interpretation of what that value is. So again, if you want to go ahead and write one, I'm going to write one. I'm going to say that 57.5% of the variation in the hard thing here is the strength. Variation in 28-day strength is explained by the 7-day strength. And then we would make a little note here that 42.5% of the variation is unexplained because of lurking variables. You know, we think about outside right now as they're rebuilding our football stadium and the stuff around it. Are they working today? Probably not. With as heavy as it's rained overnight, I notice our little fishing pond is nice and tall now. It was not much there yesterday. Now it looks like a pond that you could actually fish in. I'm sure it'd be a mess to work out there in all the mud and stuff. So pouring concrete, that would not be really that advantageous of a thing to do today, because water is going to affect how concrete cures. And so unless they can keep a lot of that water off of where they're pouring the concrete, then they really don't want to do it, because it's going to change the curing time and how long it needs to set. It'll dilute, in some cases, the concrete mix, which means it's not going to make it as strong. And so we think about our old stadium that collapsed and stuff. That was just over wear and tear as weather, made things erode on it. Then some of that could be happening in the very beginning building stage. If you don't do the concrete in optimal conditions, it's not going to dry the way it needs to do to cure the way that it needs to have. So there are some other variations there. Maybe it's the cold temperatures. Obviously, it would be rain today. Would be some lurking variables that would cause the variation. So as we look at the next part, again, they wanted you to determine the R squared value. I went ahead and grabbed the R value from these problems because, again, I'm not having you do it by hand through a long calculation, okay, for the R squared value. The only way you're doing it is doing the TI-84, doing the technology way. Type your data in, do your lin-reg formula, let it give you the value, okay? The other way is if we just happen to have just the R value. If they just give it that and they ask us to figure out, okay, what is the R squared value? Again, R and R squared, they have a relationship. R squared is technically the square of the R value. So in this case, if I want to find the coefficient of determination, which is the R squared value, all I have to do is take the R value, if I have it, and square it. That's all I got to do. So in this case, if I tell you this problem here with the unhealthy commute that we had in our previous lesson, where it was commute time and scoring a certain way on a test, we would say, all right, my R squared value is just negative 0.9805 quantity squared. And so now that just becomes a little calculator activity. We would want to use as many decimals as they give us. So as I get out of that screen, I'm going to go through and say, all right, quantity negative 0.9805 squared. And I get that my R squared value is 0.9614. I'm going to go ahead and round it to the fourth place. That's typically where I have everybody round stuff to, just because my AP class always has to do 4 decimals. So in this case, 96% of the variation in our situation there, the score on that test, is explained by the commute time, is what that means in the context of this problem. So as they say to go through and interpret it, we would say, oh no, that's an ugly color. 96.14% of the variation in the test score is explained by the commute time. .86% of the variation is due to lurking variables. And again, they ask us on their one, it says interpret the coefficient determination. We did there, and then we comment on the adequacy of the linear model. So again, for me, that strong of a negative correlation lets me know that, that is the R-squared value being high, being above 0.9, lets me know that that linear model is appropriate. I know it's a strong negative linear correlation. As the commute time increased in those problems from the previous lesson, the score on the test decreased is what ended up happening. And so that linear model was appropriate. Again, we had that other way of looking at that table where I didn't pull the thing across for this, the numbers for this one, but we would look at our sample size, whether this had like 9 or 10 or however many data points. We would say, all right, on that table from the back of the book, n is equal to 10, what was the critical value associated with it? And then we would compare it to positive 0.980. And if we were bigger than that critical value, then we said, hey, the linear model was appropriate. Okay. Next one here, if you're working ahead of me, they want us to again go ahead and find the R-squared value, and then also do the interpretation. So again, the R-squared is just taking that negative 0.9759 and squaring it. Now, do I have to put the negative in there? Do I have to put that negative in there? It helps, but again, the R-squared value should always be what type of a number? Positive. So if you forget, because a lot of times we forget to put parentheses around things when we square it in the calculator, what you just got to remember, if you forget to put parentheses around it and you put in negative 9.79 or negative 0.9759 and you square it and it comes out to be a negative number, just drop the negative because R-squared value always has to be positive. Okay? So just to show the case here, because a lot of times we get going so fast, we know it's not a hard task, and so we just get going fast. I forget to put parentheses. I see that it says negative 0.95238. I have to remember this has to be positive, so I can just drop it and don't worry about the negative in front of it and say, all right, 95% of the variation, 95.24% of the variation. I don't remember what the context of that one. Oh, credit scores. 95.24% of the variation in credit scores is due to the whatever the explanatory variable in that problem was. And again, what percent was not explained? If 95% was explained, what percent wasn't? Yeah, about 5%. It's right around maybe 4.8 to be, whatever, but about 5%. So, hey, I mean, that's pretty darn good. I think the linear model is appropriate in this situation. We do have a nice, strong negative correlation. As the explanatory variable increased, the credit score went down, okay? There is 95% of the variation is explained by that. That's great, which means there's only 5% is from some type of lurking variable, okay, which is good. I think eventually once you start seeing a bigger difference where we drop out of the 90%, we get into maybe the mid to low 80s and in the 70s, then we would say maybe that linear model is not appropriate because there is too much of a big percentage that is unexplained by lurking variables. Okay, I would feel safe. Most of the stuff in the 90% would be, hey, this linear model is good. Once I drop from the 90% as a coefficient determination, then I would probably hold off, and I would say, hey, this linear model may not be appropriate. Okay, Here's one with the weight of cars versus miles per gallon. They said, suppose we add a Dodge Viper to the data in problem 24. A Dodge Viper weighs that much, gets 11 miles per gallon. Compute the coefficient determination for the expanded data. What effect does the addition of the Viper to the data set have on the R-squared value? So I believe this was the R-squared value for this set of data. Okay, so that was without the Dodge Viper. So what we need to do is go ahead and do this real quickly, do 3425, add that to the list at 11 miles to gallon. So I tried to write that one down just to save your time on doing doing a Lin Reg twice. So if we get in here and let's get into our data, well, you know what? I'm going to reset my calculator. Second plus 712. Clear out all those columns. I'm going to go back and turn on my stat diagnostic. To me, that seemed easier than clearing each column header. So 4724, 4006, 3097, 3555, 3934, 3242, 2960, 3530, 3823, and 3425. Add the next one. Go put enter. Next one. 17, 18, 22, 19, 19, 19, 24, 26, 19, 18, 11. There we go. Oh, crudola. I don't have the same things in my columns. All right, let's see where I have my happy fingers. Somewhere I got my fingers off track. All right, let's start left column. 4724, 4006, 3097, 3555, 402. I forgot the 4029. 4029, 3934, 3242, 2960, 3530, 3823, and 3425. All right, oops. I made a boo-boo on that one. What is 3823? 3823. Oh, crud. Yes, 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 yes. All right, let's go over to this column. I forgot the first number? Sheesh. That's the bummer part compared to like our previous chapters when we're doing mean, median, mode, and all that other stuff. You could just add it to the end of your data. Here we got to make sure we're pairing X and Y variables up together. So we have to be really careful because it does affect the least squares regression line and the correlation values and the coefficient determination. So option 4, get down there, hit calculate. There we go. So without the Dodge Viper, that was without Dodge Viper. That was our R squared value. With the Dodge Viper, what's the Viper? Our R squared value is now 0.2299. And the R value is negative 0.4795. So what did it do? By putting that Dodge Viper in there, what did it do to our R squared value? Brought it down. So before, 70% of the variation in the miles per gallon was explained by the weight of the vehicle. Now adding that vehicle there, change it to where only 22% or 23% of the variation was due to the mile the variation in miles per gallon was due to the weight. We just increased the amount of lurking variable potential things that could affect stuff. Whatever they end up being when we think about miles per gallon and cars and the weighted cars, why? Not looking at what other, most of those cars look like they were probably pretty good aerodynamically, when we think about some of those designs of cars. Some of them were big cars. I mean, I just saw a Cadillac, but I don't know what brand of Cadillac that was. So some of those things, our Ford Focus is a good economical car. Ford Mustang, yes, we know it's a sporty car, but again, those are aerodynamically, wind flow wouldn't affect as much. So maybe when you think about not only the weight of the car, which is not a extreme value. I mean, the Buick LaCrosse had a greater weight. It looks like the highest weighted vehicle there. But here, this one's not that bad on the weight, but it's got horrible gas mileage. And now we say, okay, what are those lurking variables that's causing that? Is it the engine size, like type of engine? Is that one of the lurking variables that's causing that drastic of a decrease in the miles per gallon? Because right now it doesn't look like weight. Because obviously the Buick LaCrosse, heavier car by 1,300 pounds, almost a little bit more than a half a ton. It gets better gas mileage. So there's got to be something in the components of the engine itself that's causing that lower of a thing. And so now by adding that one to the mix, now we just increase the number of variation or lurking variables that cause the variation that are unexplained. All right, here's the long problem. This one's going to take us a while. Okay, this is kind of how we're finishing up for the day. This is putting kind of the whole package together. So I'm going to turn off my video here in a second, and then I'll record this one separately. But there's basically 88 data points here. That's why I'm going to say this is the last problem for the class period. Okay, it's going to take us a while to answer all these questions. We're going to go through this information about tornadoes in Louisiana in the year 2017. We're going to identify what is the explanatory variable, explain why this data should be analyzed as bivariate quantitative areas. So meaning comparing, bivariate means two variables, comparing X and Y, comparing the length of the tornado with the width of the tornado. That's why they're saying, why should we do this? We're going to draw a scatter plot. We're going to determine the correlation coefficient between the width and the length. So, and then we're going to go down and kind of get the LSRL, do some of the residual stuff that we did in the previous sections, and then go through and then wrap up with interpreting the slope, and then getting into the correlation coefficients and the coefficient of determination of what we did today. Okay, so that's going to be our last little part, is kind of do this whole package. It's going to take us about 15-20 minutes is what it's going to do. So that's how I wanted to kind of wrap up, let you start putting the whole package of this chapter together. Because all we got to do tomorrow is add one more little thing to it, okay, for this whole unit. So this kind of puts everything we've done, or we did last Thursday in class, what we're doing today, then we just got to add a little bit more tomorrow. Okay, so I'm going to